we are going to look at HCl addition to an asymmetric alkene, and in this case pi electrons are the nucleophile attacks on the electrophilic hydrogen of the HCl, and it is based on the Markovnikov's rule. If you simplify, H goes to H or rich gets richer, where the more H will get the H, right? That's also hidden idea of better carbocation is produced. So you can make primary carbocation in this case, or you can make the secondary carbocation. So we know secondary carbocation is more stable as an intermediate, so it should go more to the secondary carbocation as shown below here, right? Now the hydrogen actually went to the right on the primary and went to the left side of the double bond in the secondary carbocation. So that's again just to remind, H goes to H, Markovnikov's rule. Now as a result, what happened, we have a chloride floating around. If there's no other nucleophile hanging around, something like water available, or even better nucleophile not available, this chloride nucleophile going to attack on this empty p orbital, which is the carbocation intermediate empty p orbital. This is trigonal planar sp2. It has two sides, upside and the downside, because it's trigonal plane. You can say left and right or up and down. In this case I draw as to show you can attack with the chloride nucleophile to the bottom of the p loop. So that way it's a bottom attack, right? And then you will get the chloride attached from the bottom of the molecule or bottom of the carbocation intermediate. So that will generate a stereospecific product, or chloride is stereospecifically attached, right? Now let's see if it is bottom, so dashed line Cl, and then eventually poor little hydrogen will be pushed up, right? So that's how we most of the time we draw stereospecificity, right? Let's draw the solid hydrogen, which is I put it in white in the double bond, in the intermediate, and then here, right, in this product. So solid hydrogen, and because it's pushed up, it should be actually white hydrogen in this case, right? And I draw it in white, right? Okay, so the corner methyl is kind of not a concern at this point, but we can say if you have the chance to make the bottom attack product, you have 50-50 chance to make the left top attack. So you are making one-to-one object and image of the same product. So it's a pair of enantiomers you are making because of the ability of 50% to each side, or top 50%, bottom 50%. So that's a racemic mixture. So therefore this reaction here is non-stereospecific. So that's the key point. So stereoselectivity is not achieved, but we achieved the regioselectivity choosing secondary carbocation over primary carbocation based on the Markovnikov's rule, or H goes to H, right? That's the key point to take. Now when you draw the R and S, you can just keep a mirror in between the two molecules and copy the object to the image, and you should be able to draw R and S and show it, right? So give the priority CIP rules, and if you're not sure, watch the other video, and then you should be able to. Now I've just marked primary and secondary carbocations again because I want to talk about the energetics of it, right? So the energetics here, we are looking at the intermediate formation. So you start with the common reactant asymmetric alkene. It goes through the pink pathway to the product 1, let's say, and it through the primary carbocation. So there's a quite a large energy required for the activation energy, but the yellow path, which is the secondary carbocation, is much lower energy, right? So that's the difference. Thank you.